So that was fast. All right, everyone get that? All right. So when we talk about this oxyhemoglobin dissociation curve, this stuff in red is the answer. This is what it is. This is the percentage of saturation of hemoglobin. Percentage of saturation of hemoglobin based on the partial pressure of oxygen in the blood. So if you have more oxygen in the blood, you should theoretically, mathematically, if everything goes well, have a higher saturation of hemoglobin, yes? If you don't have the oxygen in the blood, you would have a lower saturation of hemoglobin, okay? Yeah? Great. So there's some things that change that saturation of oxygen in the blood on hemoglobin. We're going to talk about what those things are. And those changes to the saturation of the hemoglobin cause oxygen to either hang on or be let go of the hemoglobin more readily or not, depending on the situation. We'll talk about what all those are as well. And so this curve is something that represents all of those changes, the sum of those changes to how oxygen binds to hemoglobin. Okay? That's basically what we're going to be looking at with this oxyhemoglobin dissociation curve. And this will make a lot more sense as we go through. So diseases can shift the curve. Treatments, you do, can shift the curve. Different chemicals can shift the curve. Temperature can shift the curve. All these different things allows this curve to shift. So some thoughts about red blood cells, right? There's heme groups that are on the red blood cell. The heme group holds on to the oxygen, and each one of these heme groups on here is affected by this curve in some way, shape, or form. And so we can see that with oxygen on a red blood cell, what does that do to the color of the red blood cell? Makes it brighter, like a brighter red color, right? And if you don't have oxygen on there, it's sort of a darker red color, right? So if you look at arterial blood, it's sort of bright red. If you look at venous blood, it is not, which is the entire premise of how pulse oxes work. They look at the color of the red blood cell and determine exactly what the oxygen concentration should be based on that finding. So when we look at this curve, there are things that all change it around. We'll talk about what all that stuff is. You have to, for sure, remember all the ideas of how oxygen gets into the system, right? So the entire respiratory tree, oxygen gets into the alveoli, respiration occurs at that particular point in time onto the red blood cells, okay? So this saturation that we were talking about just a second ago here, O2sat is a useful tool. I don't rely on it for a hill of beans, except for understanding if there has been a positive change in oxygenation. So let's say I've got an asthmatic patient, I throw them on a pulse ox, their SpO2 is 76. And I give them oxygen, and I give them a bronchodilator, calm them down, bag them, maybe use CPAP, whatever, all this stuff, and their SpO2 comes up to 98. Have I improved this patient? Yes, you can see it, but you can objectively read a number to say that this person has gotten better. We'll talk about that with end-tidal CO2. When you do intubations, you better damn well have end-tidal CO2 on that patient as soon as possible. We used to say, before we had end-tidal CO2, we're going to look for vapor in the tube and chest rise and fall and improve vital signs and blah, blah, blah. And all those things are kind of subjective findings. Did you really see vapor in the tube? Was there really chest rise and fall? But if you have end-tidal CO2, you have a definitive number. This is what is happening with carbon dioxide being released. We can measure it. It's there. We know the tube is in the right place. This has saved paramedics' butts more than you can imagine. For the tube that gets to the ER, that might be marginal, and they say, oh, well, the tube came out, you guys didn't tube the person the right way in the field. That's what the problem is. That's why this guy's dead. Interesting, my end tidal CO2 on my monitor shows that it was 24, 30, 42 all the way until I turned over care. So what's that? Okay, it's an objective finding. Sometimes this is an objective finding. Sometimes it is not an objective finding, it's just horseshit. Right? And what situations is that? Carbon monoxide poisoning. Hands are cold, person has nail polish on, right? Say again?
Blood loss.
There is blood loss. Okay, so tell me what's happening there.
If there's not enough blood to carry the required amount of oxygen, it's still going to be saturated, but it doesn't have enough oxygen.
Right, so if I have a dramatic drop in my hematocrit, hemoglobin, right? This doesn't care about the number of hemoglobin I have, it just says whether it's saturated with something or not, right? There was just an article that came out that said that this is still not a very useful, accurate tool. Look, it's a tool, you gotta use it with all the other ones. Just keep that with a grain of salt, and I'll get off my soapbox and move to the next slide. Okay? But use it with all the other tools you have. Don't just simply rely on it, okay? All right, so a normal curve, the amount of oxygen available to the tissues. Not that it's released or not, it just says that this oxygen is on the hemoglobin and potentially available to the tissues. There are situations where it doesn't come off and it stays on the hemoglobin and the tissues don't get it, even though they should. So here's the normals for temperature, pH, PaCO2. Deviations from these norms will cause a shift of this curve and cause the hemoglobin to either let go of oxygen more readily or just hang on to it for longer. That's why we say it's potentially available to tissues, because it depends on what the hemoglobin does. It's fickle that way. The temperature's a little off. No, you don't get the oxygen today. Okay? So these are our normal values, 98.6, pH is 7.4, which is right in the middle of 3.5 to 4.5, and CO2 of 40. All right, so here's some changes that can occur. pH can go up or down. PaCO2, partial pressure carbon dioxide, can go up or down, which changes pH of being either more acidic or more alkalotic. Carbon monoxide, abnormal HGBs, temperature, intracellular compounds, and then this diphosphoglycerate. Okay, we'll talk about that in a second here too. So if we have pH change, you can see that an alkalinity causes a shift to the left, and then acidity changes the shift to the right. So the blue line is your normal curve. Lower pH causes a shift to the right. It's a high PCO2 or a low hydrogen ion concentration. That'll all cause that acidosis, change it to the right. Alkalosis, where you've got low PCO2 and low hydrogen ion concentrations, shifts it to the left. Temperature. So if you've got a decrease in temperature, it shifts to the left. Increase in temperature shifts it to the right. So here's a relationship of different temperatures. So if you have somebody that's got a little bit of a fever or a higher fever, shifts the curve to the right. And when you have a right shift, typically the hemoglobin will give off oxygen more readily, and you have a shift to the left, it'll hang onto it more readily. All right, so this is just what happens with temperature. Carbon monoxide, 200 greater times affinity for hemoglobin. It gets on there, that changes things all over the place as well. So you have lower oxygen concentrations. Overall, period, you don't have oxygen available. It's not potentially available for the tissues. It's just not there. If you don't have good hemoglobin, again, same kind of situation. You don't have the ability to bind or unbind or anything. You just cannot get the oxygen onto the cells. Diphosphoglycerate, this is an interesting substance. It's an enzyme that's on red blood cells, and it allows those cells to either hang on to oxygen or not hang on to oxygen. And so the amount or levels of diphosphoglycerate also change this curve to the left or to the right. And so if you have higher levels, changes it to the right, lower levels off to the left. Okay? So what causes these increases of DPG here? Anemia, COPD, all these kinds of different things that can cause the increases of it. And so you get more produced when you have more oxygen demand. A very interesting thing that happens in the body. And so if you have more DPG, what does it do? It allows for greater binding of oxygen to hemoglobin, and then also a greater ability to release oxygen to the tissues that need it. So in an oxygen demand scenario, you have more DPG, and then you have the ability to release it to the tissues more readily. Okay? Decreases here. If you don't have enough DPG, the body will make more red blood cells. Why? What's it trying to do? Compensate by more of the cells to hopefully create more volume and then be able to transmit more oxygen out to the cells. It doesn't work that way, though. It doesn't work so well because the new cells are weakened and they can't initially carry as much oxygen as cells that have been in the system for a little bit. Okay, so these are a lot of the things that are at play here with the hemoglobin dissociation curve. Here's pH changes. So what drops pH? So 7.35 to 7.45. Here we have a pH of 7.2, so it's lower. High hydrogen content, increased CO2 down here, increased temperature, increased DPG. All those things make the curve shift to the right. When the curve shifts to the right, it has a higher propensity to offload oxygen to tissues. So we want that. You want more oxygen to actually get to the tissues. If you give the person oxygen. If there's no oxygen in the system, is it going to offload oxygen to the cells? No. All these other things here shifted to the left. Decreased hydrogen ion, decreased CO2, decreased temperature, and then decreased DPG. So all those things will cause the curve to shift to the left. Hemoglobin hang on to oxygen. It's harder to get off the hemoglobin, and that's less protective of the body tissues, and so then not as good for them. Okay, does that make sense? All right. So let's take a look at this kind of box here. What is this telling us here? So this is PO2 in milligrams of mercury here. And so if we have a regular curve and we have, let's just say this is like what, 30 potentially, right? Amount of oxygen in the system available. This is the percent saturation. It's about 30% here. Or sorry, 50%. Right? Does that sound about right? Does that look right according to the chart for you? So when the curve shifts to the right, what happens to the amount of oxygen on the hemoglobin?
Decrease.
It's decreased. Where is it?
30.
It's in the tissues. Okay? If the curve shifts to the left, now what happens to the amount of oxygen available?
Increase.
Well, so this means that it would take less than 20% to maintain a 50% concentration on hemoglobin, right? Why is that? Because it's hanging on to it. So you don't need as much oxygen available to keep the same saturation of hemoglobin because it's hanging on to it. It's already saturated. Does that make sense? Okay, just keep stewing with it. All right, so left shift. Increased affinity by hemoglobin for oxygen. It hangs on to it. the percentage of saturation is higher. And what does that ultimately mean? The tissues are not getting it, right? So that person that has, comes out of a house fire and they've got a high SpO2, oh, it's all good. Check out the pulse ox, it's fantastic. Better than mine. Well, of course it is. Right? Okay, so that's not good. So a left shift is not protective at all. Hemoglobin hang on to the oxygen, they don't give it off to the tissues. Easier to get on, it's harder to unhook, etc. Okay, so you have tissue hypoxia, even though it appears that the SpO2 is really good. A right shift is the exact opposite. It's harder to hook on to the hemoglobin, which means that if you've given the person enough oxygen, it can unhook. It is delivered out to the tissues themselves that actually need it. And so this person's SpO2 might appear to be lower because the hemoglobin is giving it off to the surrounding tissues themselves. All right, right shift is good. Left shift, not so good. Acidic, a little bit higher temperature, higher DPG, higher carbon dioxide levels. It's a little bit more protective. It's a little bit better. The body tends towards acidity anyway because of metabolic processes, so that's an all right kind of thing. Right? Now, do I expect you all to measure this oxyhemoglobin dissociation curve? No. Do I expect you to understand it and know it? Yes. We will test it here. You will see this in airway class. You will see this in your other classes. I will guarantee it. Okay? pH balance and imbalance, I guarantee you're going to see that on some quizzes down the road in your paramedic classes here. So, understand this stuff. If you need help with it, reach out. Okay? All right, that's right shift. Example of that, and so here's just some other curve pictures, etc. Blah blah blah. All right, you guys get it? Does it make sense? What does the oxyhemoglobin dissociation curve represent? Without looking. Mathematical percentage saturation of hemoglobin based on oxygen available in the system. So the more oxygen available, technically, the higher the saturation is going to be, given everything is within normal bounds. If things go out of bounds for any of those reasons, you know which way the curve is going to shift. If you have acidosis, it shifts to the right. And is that better or worse for the patient?
Better.
Why is it better for the patient?
More oxygen to the tissues.
Hemoglobin are releasing more oxygen to the tissues if you have given them oxygen to release. Okay? All right, left shift is like an acidosis, low temperature, low DPG. All those things are a little bit worse because then the hemoglobin hang on to the oxygen. You don't release it to the tissues. What needs it more, the hemoglobin or the tissues? The tissues. Okay? All right, good.
Question, Dave.
In those cases, will you still be seeing like physical signs of hypoxia then, even though
Yeah, sure you could.
Okay.
Mhm.
You still might see like cyanosis, altered mental status, and such.
Potentially.
Yeah.
Even though they have a higher. Okay.
You can see those things because you really got to look at the tissues, what's happening with the tissues. So again, when you look at the body and do your assessments, why is the body reacting the way the body's reacting? So it's not right here, right? So look at the environment, look at the conditions, look at what's going on with the patient, try and understand, all right, what's happening with hemoglobin and why are the numbers the way that they are. Looking at end-tidal CO2, SpO2, all the other things. What's the blood pressure? What's the pulse rate? What are the other vital signs? you know, how the lung sounds, like all those different things are gonna play into all of this. Okay? Sorry.
For like, when speaking of this, does that relate to like why like, I know we say like in sepsis patients it can be like more dangerous if they're colder. Is that a shift in that, or is that just like them getting no longer compensating for not like acidity? It's not like an alkalosis shift.
So if the temperature drops,
Mm-hmm.
then, well, there's a couple of things. One, they're not perfusing,
Right.
and they're hypovolemic,
Okay.
right, in addition to being hypotensive because of fluid shifts, but then that also shifts the curve to the left,
Okay.
which is not protective of tissues, and oxygen maintains on hemoglobin.
Is that why it's like more of like a, I mean, I guess a risk of like the sepsis patient is cold versus not?
Well, if they're cold, like it's more of a hypotension, hypovolemia kind of issue,
Okay.
but a result of them also being cold are these other things, which is not helpful in any way.
Okay.
Right? Especially if you're hypotensive and you're not perfusing, then to not give the tissues the oxygen because the hemoglobin is like, nah, I'm gonna keep it. That's not beneficial for tissues, even as you're compensating.
Okay.
Okay, that's kind of that spiral happening. All right, so let's take a look at acid-base balance here. So we've talked about homeostasis, we've talked about electrolyte movement, we've talked about water movement, and all of these things have this play on what happens with acid-base balance in the system here. And so we try and operate here in the 7.35 to 4.5 range. And so this is a logarithmic scale. What does that mean? It does not mean 2 is twice as much as 1 and 3 is 10 more than 2, right? This is an exponential scale. And so it's an exponential log moving up this scale there from 1 to 14. And so acidic means more hydrogen ions. That will create the acidity. And what's odd about this and the way it sounds is that drops the pH. So if you have a lower pH, you have more hydrogen ions. Okay? Yeah?
Yeah.
If you have an alkalinity, or you're on the alkalinic side of things, it's fewer hydrogen ions. So more hydrogen ions, low pH, fewer hydrogen ions, higher pH. Higher pH is alkaline, lower pH is acidic. Okay? Some of the things that you drink, like the colas and whatnot, they're very acidic, but it's masked by sugar. And so it's a little bit of a balance that I'm using sugar in a high acid environment. Why is it so highly acidic? Because that helps to reduce the pathogen load in the drink. So if you look at foods, they try and either put in a kind of a preservative or make it more acidic so that there's less pathogen load in them. So when we talk about the body, we're going to talk about this average range of 3.5 to 4.5, somewhere right in the middle there. Y'all need to know this. I'll ask this on a quiz. You'll see this down the road, the carbonic acid system here. And so right in the middle of this buffer system, we've got carbonic acid, H2CO3. If you've worked with equations before, nothing is gained or lost. So if we look on the left side here, we've got 1 C, 2 oxygen, 2 hydrogen, and another oxygen, right? So that means we have 2 hydrogen, 1 carbon, and 1, 2, 3 oxygen. You see that? Okay? Add these all together, this is what you get. These also break down then into 1, 2 hydrogen, 1 carbon, 3 oxygen. So hydrogen ion and a bicarb ion. These are ions because they are positively and negatively charged. So now you can move back and forth across this buffer based on the circumstances in the body as to how many hydrogen ions you have, how much bicarb you have, to how much carbonic acid you can create, and then how much of that carbonic acid can be broken down into water and carbon dioxide. On one side of this, we have the lungs, which is where you can add or get rid of carbon dioxide and water. And on the other side, you've got the kidneys that can flush or flush hydrogen ions or create bicarbonate ions to combine with the hydrogen and create carbonic acid, which can then be released by the lungs. Does that make sense? Good. You guys should have gotten this in A&P, right? This is all just review. Am I going too slow for y'all? No? Okay. All right. Okay. So this is the extracellular buffer system. If you look at this system, it can really readjust the pH in seconds. So when you're out of shape, walking up the stairs, from the parking lot into the building, and you feel the burn in your legs, right? That's acidic lactic acid in there. That's a change. You feel the burn is the feeling, the acidity, and after you rest, some of that lactic acid gets flushed out, and this buffer system has changed around some of those acids in there as well, and then move things around in the body as you sort of get yourself back. Not all of it, but to some extent, some of that's happening. So respiratory system adjusts in minutes on one side of it, but the kidneys can't just get rid of a whole mess of hydrogen ions and create bicarb in a short amount of time. And so it takes a longer time for the kidneys to react on the other side. And typically we call the lung side of things the respiratory side, and the other side the metabolic side. So when the kidneys are getting rid of hydrogen ions or creating bicarbonate, that is considered on the metabolic side of it. So when we talk about something being acidic or alkalytic, we also add a caveat of whether it's in a respiratory state or if it's in a metabolic state. Okay? All right, so we've got this balancer. We want this pH to be right in the middle, 7.40, and it can swing a little bit based on the number of hydrogen ions. The number of hydrogen ions tells you whether it's an acidic or alkalytic environment, because they directly relate to pH change. So if I have somebody that's 7.35, is that more acidic or alkalytic? Acidic. Someone that's 7.45,
Alkalinic?
more alkalytic. Someone that's 7.2,
Acidic?
acidic. Someone that's 7.5,
Alkalinic?
alkalinic. Okay, so you all have half of this figured out already. Okay? The other half is not so hard, although it appears to be, it's really not. So when we look at now where the problem is with an individual in figuring out why their acid is normal, high, or low, it's either a problem with the lungs or the respiratory system or a problem with the metabolic system. Okay, right now everything looks pretty good. It's all moving back and forth. It's happening right now while you're sitting there. If I have an asthma attack, reaction, whatever, or someone, I'm choking on something, or doing cardiac arrest, or in some way, shape, or form, stop the movement of oxygen in and carbon dioxide out, where is the problem?
Respiratory.
Respiratory system. If I have kidney disease, diabetic ketoacidosis, dehydration, other kind of issues, where's the problem? Metabolic side. If I have a problem in my lungs and can't convert and get rid of CO2 and H2O, what has to pick up the balance of the change of things? The
Kidneys.
metabolic side. And how fast does that happen? It does not happen fast. Okay? If I have a problem with my kidneys, or there's a metabolic issue in the system, what has to pick it up? The
Respiratory.
respiratory system. How fast can it do that? In minutes. So we used to, in cardiac arrest, say, oh, this person is really acidic because their heart hasn't been pumping and they need to get oxygen. And so we used to bag the snot out of people, right? As hard and fast as we could, we would bag people. And so on one hand, yeah, we're getting oxygen in, as long as we're doing good CPR, which was sort of up in the air. But on the other hand, you gotta get carbon dioxide out, right? Otherwise, too much carbon dioxide in the system makes people more acidic, right? Because you're not getting rid of it, it converts to carbonic acid, which then devolves into hydrogen ions and bicarbonate ions. And so, higher hydrogen ion concentration makes people more acidic. So we would bag people to death, literally. And that wasn't helpful at all, right? But we could make dramatic changes in somebody just by bagging them. So if you have someone that's on the borderline of being really acidic and you can bag them really well in a normal kind of way, you can turn that acidity around fairly quickly within 5 minutes, 10 minutes, so they're not in an acidosis anymore. You can also, as what we were doing, put them into an alkalosis. What happens if I bag the snot out of them and get rid of all the CO2?
You're gonna make them alcoholic.
pH goes up, which is alkalosis. So I can create a respiratory alkalosis just by hyperventilating somebody, which is exactly what hyperventilation is, a respiratory alkalosis.
But what if you still have the metabolic acidosis at where it would just be the respiratory?
Yes, you would still have that going on. So it's a degree of how much you're affecting that particular metabolic acidosis. But they would be in a respiratory acidosis to start, which would then transpire into a metabolic acidosis at some point. Okay? All right, y'all are with me? Make sense? Getting it? You got it so far? Okay. All right, so respiratory regulation, several minutes. We talked about all this stuff, blah, blah, blah. Renal control of hydrogen ions, so we'll get rid of hydrogen ions. They'll also create bicarb ions, takes several hours, etc. Blah, blah, blah. So here we are, acid-base balance and imbalance. You already worked out half of it where you know that if there's a high amount of CO2, that's an acid, high amount of CO2, pH change. Let's start there. I apologize. I'm getting a little ahead of myself. pH change. If the pH is high, that's a alkalosis. If it's low,
Acidosis.
don't get that wrong ever again, okay? If you understand it, you know what that is. If the pH is above 7.35, it is tending towards alkalinity. If it's below 7.35, it's tending towards acidity. You've got half of it. All right, so respiratory acidosis, if it's a respiratory problem, what happens to the amount of CO2?
Increases.
Goes up because you can't get rid of it. So if you have if you look at an ABG and you have a high amount of CO2 and you've got a low pH, the low pH is the acidosis. The high CO2 indicates it's a respiratory issue, respiratory acidosis. The respiratory side is the reason for the acidosis. Make sense?
Mm-hmm.
Okay. Respiratory alkalosis. Higher pH means it's an alkalosis. Lower CO2 means you're blowing it off. You can't blow off CO2 through the kidneys. If you could, there are other problems and you don't have to worry about this. So again, the respiratory system is the cause, and that's a respiratory alkalosis. And so when you blow off too much CO2, that's hyperventilation. Unless the paramedic provider is bagging the snot out of you, okay? All right, metabolic acidosis. Again, pH is down, that's the acidosis. You see an increase in bicarbonate or a decrease in bicarbonate. In this case, we see a decrease in bicarbonate, okay? There's a metabolic issue. The kidneys are getting rid of hydrogen ions. And so what's left is combining with the bicarbonate, so it appears that the bicarbonate is dropping. So we've got this metabolic acidosis, and then metabolic alkalosis is the exact opposite. Now, what do you notice as a trend in this graph here?
With respiratory, it's opposite, unless, metabolic is the same.
And the it is the movement of the arrows, right? Okay, so in respiratory cases, you can see that the CO2 and the pH are going in different directions. And you can translate CO2 into the metabolic sides of things over here. Bicarb going down, CO2 will go down. They're going in the same direction, that's metabolic. Okay? And we'll talk about why that happens. You guys got this? Okay? All right. When we talk about whether someone's compensating or has decompensated or is not compensating, we're talking about the range of the pH of where they are. So if the pH sort of stays within that 7.35 to 7.45 area, they're compensated. It hasn't gone out of range so much. A little bit, not terribly much, so it's considered compensated. Once it goes out that 3.5 to 4.5 range, they're now decompensated. So that's just a good way of looking at how that is. Falls out of that normal range. All right, so causes of acidosis. On the respiratory side, increased PCO2 because of slow, shallow respirations, COPD, asthma, respiratory congestion, mucus plugs, all kinds of anything that reduces the ability of the body to get rid of CO2. So we're retaining CO2, increases the partial pressure of CO2 in the system, converts to carbonic acid, converts to increased hydrogen ions. That makes them really acidotic. Okay? On the respiratory side. On the metabolic side, we've got a decrease or loss of bicarbonate ions. And so for some reason, we don't have the bicarbides. It could be because they're combining with hydrogen ions. It could be because the kidneys aren't creating them. It could be because the system is so acidic. So an aspirin overdose. What's aspirin? What is the actual name of aspirin? ASA, what does that stand for? Acetylsalicylic acid. Right? So if you have someone that's taken too much aspirin, they can create a metabolic acidosis because they have acids in their system. Okay? Large amounts of acids otherwise, lactic acid, ketoacidosis, renal disease, all these things are acids in the system, and they will eat up the bicarbonate that's there and cause a metabolic acidosis. Because you don't have the bicarb to combat that much acid in the system. Okay, you all with me? So this is acidosis, respiratory and metabolic. All right, what are the effects of this? All this bad stuff. None of that's good. So when you see someone in DKA, what's happening?
Small frustration.
Okay, what's happening?
Oh, you're off gassing.
Why?
Because they have a buildup of acid and it's releasing it. It's getting rid of that CO2, right?
Okay, so what's the it's?
But
You're correct. Just put nouns in place of the pronouns.
it's getting, so they're getting rid of the CO2. They're,
The body is getting rid of CO2 by increasing respirations
Yes.
because there's so much CO2. What you're doing is you're getting rid of hydrogen ions because it's converting carbonic acid, which is converting CO2, and you're getting rid of that. Okay? So for someone that's in DKA, what happens? The cell can't get what in? Can't get dextrose in because we don't have insulin, right? And so what happens outside of the cell? What's conglomerating out there? Sugar, right? And so it's hypo or hypertonic outside compared to inside. Hypertonic outside the cell of sugar compared to the inside of the cell. And so the inside of the cell goes from what kind of respiration? Aerobic respiration, which is highly effective, to anaerobic respiration and or the breakdown of fats, right? Because you don't have glucose with oxygen for the right aerobic process. You could have plenty of oxygen, but if you don't have sugar, it's just not going to work, right? All right. And so what are the byproducts of anaerobic respiration or the breakdown of fats, or looking at some of the other processes there? Yes, and ketones, right? Reduced ATP, so lots of acids. And so how does the body deal with all these acids? It tries to increase bicarb production, but you still can't get enough bicarb production done, right? And so we convert some of these things out to higher amounts of CO2 and water. And so what does the person do? First of all, they're really thirsty because the body's dumping hydrogen ions and trying to get rid of the excess sugar, right? And so they'll do a urine dipstick and see how much sugar is in the urine if it gets really bad. And so getting rid of water, so the person's dehydrated, plus the extracellular environment is really hypertonic, and so you have a shift of water into that interstitial space to account for it. And so the person is really thirsty, drinks a whole lot of fluid, and is peeing a whole lot of fluid out, plus they're really hungry. And now they go into these Kussmaul respirations because they're trying to get rid of the extra carbon dioxide because of all the acidic production. Yeah, you guys are with me? Does this all make sense? All right, so that's why in TKA you have deep, rapid breathing, because you're trying to get rid of all of the excess carbon dioxide. What else are you going to smell on that person's breath? The ketones, because of the alternate energy production pathways. Okay? All right, good. So that's effects of acidosis. Alkalosis. So this is on the other side. So decreased PCO2, hyperventilation, getting rid of it, right? So you've got a decreased PCO2 because typically of hyperventilation. You could also have a decreased PCO2 if you have what? Excess bicarbonate. If you have excess bicarbonate, it combines with hydrogen ions, and so you don't have conversion to carbonic acid and then production of CO2 and H2O. So it's on the metabolic side, right? Increase in bicarbonate ions. See that? Does that make sense? Okay? Lots of hydrochloric acid, lots of acids from the system. So people that diarrhea and vomiting, they get actually rid of a lot of acids that way, and that can put a person into a metabolic alkalosis. Head injuries, brainstem tumors, these usually lead to, on the respiratory side, changes in respiratory patterns. And so those changes in the respiratory patterns lead to an inefficient ingress of oxygen and off-gassing of carbon dioxide. All right, so these are all causes of alkalosis. I had a partner that had stomach problems, and he popped antacids all freaking day long. It is amazing to me that this guy was breathing, honestly. I still think he was living in a metabolic alkalosis, but there you go. So that can happen as well for folks. So if you have a patient, what's that?
You can't overdose on Tums, right?
Well, you can overdose on anything.
Like you can take a lot of Tums, right?
You can eat a lot of Tums. Maybe cut back a little bit.
I was saying when I was pregnant, I would pop those things like candy.
Sure.
Literally, like,
Yeah.
go through a pile of Tums a day.
Yeah. No. You were making yourself a little bit more alkaline. Not in such a way that it affected you negatively.
No, I didn't think so, but now you had me overthinking it. Like,
No, don't overthink it. But if you have someone that is not healthy and not well, and they're just eating tons of antacids, you can see how it puts them in a metabolic alkalosis, or could tend them towards that. Okay. here's all the effects of an alkalosis. So when you see someone that has, we talk about people that are hyperventilating, right? And they start having that tingling around the mouth and in the fingers and some tetany and they can't release and they're just really anxious. All that stuff are effects of alkalosis. So how do we combat that kind of alkalosis? Respiratory alkalosis.
Calm their breathing.
Say again?
Slow their breathing.
Slow their breathing down so they're not blowing off CO2. Nothing? What do you guys got? Hmm? Oxygen's not the problem. What's the problem? They have plenty of oxygen. They don't have plenty of carbon dioxide. How do you get carbon dioxide back in the system, aside from giving them a non-rebreather of carbon dioxide?
Paper bag.
Paper bag. Have them rebreathe, right? So how much carbon dioxide do we exhale in a breath, right? This is the whole idea where CPR works when you do mouth-to-mouth on somebody and you don't put them on oxygen, right? We exhale an amount of oxygen and a whole lot of carbon dioxide. And so if we can rebreathe that carbon dioxide, that helps to get it back in the system. Now, don't withhold oxygen from somebody when you're doing this. You want to still give them some oxygen, but for them to calm down and rebreathe some carbon dioxide is very helpful. We used to carry paper bags in our drug boxes just for this. Yeah, absolutely. Yep, breathe in a paper bag. Rebreathe the carbon dioxide, increases your carbon dioxide levels, reduces the respiratory alkalosis back to normal. Yep. Okay. All right. So here's this balance. You have to have a 20-to-1 bicarbonate to carbonic acid, something you're not going to necessarily be able to measure at all in the field, right? And here's just sort of a picture of a regular kind of system. We've got metabolism occurring at the cellular level, creating hydrogen ions. That is a tendency towards acidity. Kidneys are going to create bicarb that's going to match with that hydrogen ion in a balance. It's going to create carbonic acid, which then gets released, or which gets moved into being carbon dioxide and water, which then gets released by the lungs. Okay? In a carbonic acid, if it's high, we've got high amounts of acid, so you have a high amount of CO2, you have a high amount of hydrogen ions. The kidneys are going to try and flush the hydrogen ions out. There's too much hydrogen to match with the bicarb, and so the person's in an acidic environment, whether it's respiratory or metabolic, and so you've lost this 20-to-1 ratio, and this is where you are. So the body's going to tend towards trying to create more bicarb and blow off the CO2 so that it can't reverse direction and create more hydrogen ions. Okay? If the carbonic acid is low, that means you don't have high amounts of CO2, you don't have high amounts of hydrogen ions. The body's not going to try and get rid of it, it's going to try and keep them down in the kidney level here. It's still going to make bicarb, but now you have too much bicarb to hydrogen, and so you're in an alkalotic state. So you've got a reduced carbonic acid. And you're not going to blow off CO2 and H2O. In that case, you're going to try and keep it. All right, good? Okay. Don't worry about that. This is a good way of read through this where you can see this is consistently happening where this buffer system is occurring at all these different levels, right? And it's continuing to occur. That's why it's really important, and I will advocate this all day, every day, that you use not only your SpO2 to see if the person's getting oxygen at some point, and if they haven't lost blood, they're not bleeding, they're not having trauma, chances are they've got hemoglobin. If they don't have some kind of disease, to not have hemoglobin or have hemoglobin erect in some way, shape, or form. So you can see the oxygen coming in, but you've got to use end-tidal CO2 to see if the person is getting rid of carbon dioxide. If you're not getting rid of carbon dioxide, why? And if they're not getting rid of carbon dioxide, it's being retained, which makes them more acidotic. Is it a respiratory issue? Is it a metabolic issue? You'll find out the metabolic issues by your patient assessment and the respiratory issues by your interview of the patient history and medical history, and whether it's a respiratory issue by your assessment and vital signs and all this other stuff that's going on, they'll be tired. So you gotta put end-tidal CO2 on your respiratory patients and see what's going on. Now, when you put the person on end-tidal CO2 on the monitor and it reads 20, is that in or out of bounds as to where it's supposed to be? What's it supposed to be? 35 to 45, right? And so it reads 20. So what does that mean? They're retaining CO2. Remember, you're assessing them off gassing. You're not assessing an ABG. So if it's low coming out, it's high inside the body.
It's going to be an inverse correlation then.
Correct.
Okay.
So
The other day you tried to tell me that it was a direct correlation.
It is
That doesn't
not.
make sense though.
it is not. Okay? So if there's another way of looking at it, right? So if the person is hyperventilating and you've got a high amount coming out, it's got to be low inside the body. Unless you're at that point where they've gotten rid of so much they don't have any else to give, right? And you've got good, you can see the respiration's occurring. There's no problem with the lungs. You're getting rid of, you're moving air, right? Why else could it be that their end-tidal CO2 is normal to lower, and in that case, they don't have the reserves, right? So, but if you have someone that's asthma, COPD, emphysema, pneumonia, bronchitis, whatever, and they have a low end-tidal CO2, they can't get rid of the CO2, they're acidotic. And because this is a respiratory issue in origin, it's a respiratory acidosis. You all with me? Okay, great. That's that. You want to take a quick break, or you want to keep going to imbalances?